So in general, there are two types of telescopes, and I'll go ahead and throw those up here. The two types of telescopes are reflecting telescopes and refracting telescopes. And in general, what they do basically is gather photons. They are photon buckets. And the three main reasons you use a telescope is to gather those photons so the image is brighter. You are be able to resolve, see detail on an object, and to see objects that are far away. Okay, so gathering light to enhance those three different areas. So reflecting telescopes, if you think reflection, you probably think mirror, and you're right. So reflecting telescopes actually use a mirror, and I kind of hold my hands up like this because basically light is gathered by a mirror and brought back to a focal point in front of the mirror. Refracting telescopes actually use the phenomenon of bending light, and they're very much like your eyeglasses. So basically, light comes through a lens and it comes back to a focal point. That is a refracting telescope. So those are the two basic types. Now, the deal is we can have telescopes that are sensitive to various wavelengths. And I've got a kind of a slide or a figure from your textbook to show that. So one of the main things is to be able to see detail. Gathering that light and to what we say resolve an image. The detail that we see in an object is related by the angular resolution, that the amount of distance that can be resolved. So remember when we talked about your local sky and we said that you can say how objects are in your local sky by kind of holding up your hand. So it's that angle that we're trying to get smaller and smaller to get finer and finer detail. So a small angular resolution means that you see a lot of detail. So in general, if you take the mirror of your telescope, of a reflecting telescope, or if you take the lens of your refracting telescope, and the larger you make it, basically the more photons it's going to gather. So the bigger the better in general for all of these aspects of using a telescope. And in general, if you double the diameter, you're going to double the details that you can see. Angular resolution talks about details that you can see. And I like this. Let's see what you think of this little video. You've maybe driving at night kind of witnessed the same thing. Let's see. Where you see a car in the distance and you can't quite, it's probably a car, and cars have, if they're working right, two headlights coming at you, but you see it as one headlight at first. And at some point, it gets close enough that you see the two headlights resolved from the one. One of the things in observational astronomy, there are a lot of folks out there that enjoy looking at pairs of stars called doubles. And so there is a famous double in the constellation Lyra. It's called Epsilon Lyra, and basically it's a quartet. So what looks like one star in a nice telescope, you can see actually kind of two stars, but if it's really nice seeing, you can actually see that those two stars separate into, each one of those have a pair of stars. So it's called Epsilon Lyra quartet, angular resolution. So let's go ahead and show you this one. So that was showing you how you can kind of resolve one big blob of a headlight into two headlights as the car approaches. So this one is showing you kind of what I was telling you about, a pair of stars. And depending upon your telescope, the quality of your telescope, and quite frankly, the diameter of your telescope. So the way this works is the bottom, I can change the diameter of the reflecting telescope. It says a mirror down here. So right now it's 0.1 meters. I'm going to up it to 0.44 meters. Okay, so 0.1 to 0.44 meters. Notice that the blobby light has gotten smaller. It's gotten tighter. Okay, I'll go ahead and increase that to 1 meter. You can almost start to kind of see double lobes there. Increase the size of the mirror at 2.5 meters, and we can clearly see 2 stars. Okay, increasing it to 4 meters, 5 meters. Okay, they're just intense dots now. We have gotten more and more and more detail as we increase the size, the diameter of the telescope. Okay, so refracting telescopes then use lenses, and I think I mentioned that basically they bring the light back to a focal point behind them. The term refraction means to bend light, okay? And the thing doing the refraction is, of course, the lens, but light, in general, electromagnetic radiation will be bent or refracted as it leaves a medium. And so here, it's going from air to glass. Okay, and can you see the light being bent? And then actually here, it's going from glass back to air. Okay, and it's bent again. So it's bent twice. It goes from air to glass, glass to air. Okay, so, but our telescopes actually use lenses that are what we say convex on both sides. Okay, so it's kind of bowing out on both sides. So light then is bent twice, just like with the plain slab of glass, but it's bent specifically to come back to a focal point. And then right here, this would be like within the tube, the telescope tube, this is where all the information is stored. I just think that is so cool. Okay, and then that information is unpacked for us to see it in an eyepiece. So this is road trip. This is a very wonderful telescope located not far out of Chicago area, north of Chicago area. It's the Yerkes Observatory, and the diameter of this lens up there and is as big as you can get it. It's 1 meter, so a little over 3 feet. The problem with lenses is that glass over time actually will kind of deform, because you can, if it's a refracting telescope, you need to support the lens only on the edges, or you can only support it on the edges. So there's a limitation to the size. So that's gathering light somewhere in this long, beautiful tube, gathering light back down to here. So I don't know if you can see that, but there's a person there, and actually there's a person right here to kind of give you scale to the optical tube. So this is a wonderful dome that it's housed in, and notice that here's the slit, and actually this dome can kind of move around so they can put the slit where they want it in the sky. So a beautiful refracting telescope. The reflecting telescopes then actually use a mirror kind of at the back of the optical tube, usually. And so here we see, and the shape actually now is not convex, it's actually concave. And ideally, it's a parabolic shape, but oftentimes it's spherical because that's easy to make, and it needs to be corrected then on the front end. But anyway, light comes down, and since it's not flat, it's got this curve to it. That light is actually then all brought to, again, another focal point. Now, I'm not going to go into it this semester, but basically we have different reflecting telescopes then as to how do you get to that information? Where is that information directed? And usually there's a secondary mirror involved, and it kind of directs it either out the side or out, which would be a Newtonian design, or back out the back again, which would be a Cassegrain. Prime focus, somebody sits right there. But this is a reflecting telescope. The thing about reflecting telescopes is you can make them as big as you want, because basically you can support that back, you know, till the cows come home. And actually the quality of glass doesn't matter either. So it just needs to be nice and silvered. So here's an example of a reflecting telescope, and back here you see this is the kind of the back of the telescope, so light is coming in the tube like this. Okay, this is actually a Cassegrain type design, and so I mentioned there's usually a secondary mirror. This is the secondary mirror right here, and this has a shape so that it continues to gather the light back to a focal point here, back out the center actually of the primary mirror. Okay, so this is a Cassegrain design. Another road trip. Okay, so here's a twin Keck telescope there in Hawaii. And can you kind of see the segments here? These are like six-sided little hexagonal pieces of glass that actually, I have a slide here to kind of describe something called adaptive optics, and it can actually probably kind of adjust as need be. So this actually is another type of reflecting telescope. It looks humongous, okay? And one of the reasons it's humongous, it's catching this big cousin, okay? This radio wave, which is one repeating unit, is just humongous. So, and it's a reflecting telescope. Can you see up here is where the information is sent, okay? Is focused to, I guess I should say. So here's my pitch to just kind of give you a 2 cents with regard to telescope. Buying your own telescope, perhaps, or maybe you have your own telescope. But you might try binoculars first, just to kind of find your way around the sky. The thing about using a telescope is that you either need to be able to kind of what we call star hop. You can see these pairs of stars and what you have. You can look at a sky map and your thing of interest is kind of maybe a third of the way down. And so you kind of hop to your object from the stars that you can see. Or you need to have a telescope like we use at school where you calibrate it and you tell it where you want it to go next. There's advantages to both. But it takes a while to kind of develop your technique of finding stars. Or using a telescope. So I would generally don't get hung up on magnification, because honestly, the magnification is kind of tied up in the eyepiece. And what you need to do is make sure that your lens or your mirror that's gathering the photons is decent quality and of the right, that says aperture, the right diameter, that to kind of do what you want it to do. Do your research ahead of time and just have fun with it.